Well, thank you for joining what I think will be a very interesting and important webinar. My name is Eddie Isaacs, and I'll be your moderator for this webinar. So the format for today, I will introduce the session and then each of the speakers in turns. They'll have up to 30 minutes for their presentations. We will take questions for clarifications only after each presentation. And when you ask your question for clarification, please indicate your question, that it is for clarification. The two presentations will be followed by a panel discussion with both speakers for about 30 minutes, which I'll moderate. The title of the webinar is The Role of Hydrogen and Methane Emissions Reductions in Achieving Net Zero by 2050. In Soheil Asgarpour and David Lizelle, we have two of the most prominent experts on methane emissions and hydrogen in Canada. But one may ask, what is the connection between hydrogen and methane emissions that come from natural gas? Hydrogen already is an important part of the global economy for the production of fertilizers and certainly for use in oil refining. Almost all, about 95% of that hydrogen is produced from fossil fuels, most commonly using steam methane reforming of natural gas. And even if we are able to economically capture all the CO2 from reforming of natural gas to hydrogen, and that's a big if, we will still be dependent on natural gas being clean. I'll define what we mean by clean. Methane, the main component of natural gas, has a global warming potential of about 30 times that of CO2. This has taken over a 100-year period. If there are leakages in the system during drilling, producing the gas, processing, pipelining, and distributing the natural gas, then the hydrogen from natural gas, the so-called blue hydrogen, will be carbon intensive and harm the climate. In fact, 3 to 4% of methane leakage makes natural gas no better and even worse than coal. So in summary, reducing methane emission is critical for making hydrogen from natural gas a pathway. And it's going to be an important pathway for achieving net zero by 2050. So that was by way of a short introduction. And now I'll introduce our first speaker. It is Dr. Soheil Asgarpour, the President and CEO of Petroleum Technology Alliance of Canada, or PTAC for short. Soheil has an exceptional background in energy and environment technologies, having served in executive positions in industry, government, research-intensive organizations, and industry associations. Soheil, please go ahead with your presentation.
Well, thank you very much, Eddie, for a great introduction and setting the stage. Really appreciate that. Thank you. Good morning, good afternoon. It is my pleasure to talk about various methane detection technologies, including spectrometers, laser-based sensors carried by light airplanes, drones, and super sensitive stationary sensors and cameras we are using to collect tsunami of methane emissions data. By developing statistical and simulation models and later on using machine learning and artificial intelligence, we are getting insight about the trends in methane emissions from various sources. This essentially enables us optimizing the implementation of new technologies in fugitive emissions management programs to achieve mitigation targets at the lowest cost and guiding technology development and commercialization. As you know, methane emissions are the major source of greenhouse gas emissions in producing oil and gas. So in addition, I will present the numerous developed, field-tested, and demonstrated technologies through PTAC's consortia, which collectively have the capacity to reduce the oil and gas sector's methane emissions by more than 45%. These technologies are not only currently reducing methane emissions in Canada, but also they are helping global reduction of methane emissions. Our grand vision is to build enough technology capacity to reduce the oil and gas sector's methane emissions by 90% of the 2012 level by 2030 at the cost of less than $5 per ton of CO2 equivalent. For those of you who don't know about PTAC, it's a not-for-profit neutral organization that coordinates, manages, and facilitates collaborative research and technology development, demonstration, and deployment to maintain improve the environmental and safety of performance of the gas hydrocarbon industry. So this is kind of some of the technologies that we are using in terms of where we are trying to be. So for many years, the global impact of methane emissions remained under the radar because it is odorless and colorless. However, technology have changed this concept and perception. For example, the analysis of satellites imagery data by CARES indicates that the largest sources of emissions, as you can see from this map, are essentially operations in Russia, the Middle East, African countries, and the US. And of course, the US emissions are mainly coming from the tight oil and gas production, and it's about unburnt methane from flared gas. Methane is the second largest greenhouse gas. The current annual global methane emissions are around 570 million tons, of which approximately 40% of the emissions are derived from natural sources. That would be sources like wetlands and forest fires, etc. 25% is from agriculture, 23% from oil and gas, and the remainder from landfills. The impact of various greenhouse gas emissions and greenhouse gases is determined by the duration of time they remain in the atmosphere and their ability to absorb energy. Although methane has a much shorter lifespan, I mean, if you look at it, is around 12 years compared to centuries for CO2, it is by far a more potent greenhouse gas. To estimate methane's effects on global warming, the most commonly used method is the global warming potential, GWP. Eddie actually mentioned this. This method considers methane to be equal to somewhere between 28 to 36 tons of CO2 equivalent if you are looking at it over 100 years. But let's look at it over just next 10 years. It's 90 times. And why I'm saying that, because the IPCC has stated that the next 10 years will be the most crucial in controlling climate change. So if you look at it during that 10-year period, then essentially the impact of methane becomes almost equal to the impact of CO2. So it's extremely potent, as I mentioned. The breakdown of Canada's greenhouse gas emissions by sector is shown here in CO2e, and oil and gas emissions is 26% of the total emissions. And for further breakdown and looking at various hydrocarbons, etc., here you can see conventional, including tight oil and shale gas, is approximately has the same greenhouse gas emissions as oil sands. Sources of methane emissions are fugitive, which is unintentional, and venting, which is intentional. The largest sources are venting from oil and condensate tanks and pneumatics, etc., which actually our current studies indicate that this information gotta change because we are seeing that more impact coming from oil tanks and condensate tanks than pneumatics, etc. So those studies are gonna be public very soon. So I think also I should say that methane vented from oil and gas affects not only our environment, but also our health. This sounds daunting, but reducing methane emissions provide tremendous health, environmental, and economic benefits. And talking about economic benefits, I think reduction of methane emissions is the fastest and most cost-effective approach in reducing greenhouse gas emissions globally. Methane, unlike CO2, has commercial value. We can sell methane. The cost of CCUS in reducing CO2 starts at around $50 per ton for CO2 and can increase to over $170 per ton. Conversely, methane starts at a negative cost because we can make money and increases to a fraction of minimum cost of $50 per ton of CO2 equivalent. Majority of technologies we have developed, their cost is less than $5 per CO2 equivalent. Methane is the key to creating a clean Canadian oil and gas brand. Methane reduction allows more natural gas to be sold for profit while simultaneously improving our environment. Finally, methane is the catalyst where traditional oil and gas and leading-edge clean tech meet. It has the potential to forever change how we do business by helping the small and medium-sized clean tech companies prosper nationally and internationally. And later on, you can see our game plan to do so. According to the International Energy Agency, IEA, the future of electrification is here, and natural gas is going to play a very important role in supporting the energy transition. The IEA expects that the demand for natural gas actually for generating electricity to go up by 25% by 2050. Eddie actually articulated really well. I mean, natural gas can be converted to hydrogen or can generate clean energy, but the key is to make sure that we are going to reduce methane emissions from production, processing, and transportation of natural gas. So let's talk about PTAC's initiatives. More than a decade ago, we started working on initiatives to reduce methane emissions. We formed the Methane Emissions Reduction Network to be an innovation network with a vision to build methane detection and mitigation technologies with the goal to help build enough technology capacity to reduce 45% of the 2012 level methane emissions at a cost of less than $5 per ton of CO2 equivalent by 2022. Actually, we have achieved that target now, and 90% by 2030. The network developed a technology roadmap. It connects people, ideas, projects, technologies, capital. It works in collaboration with Clean Resource Innovation Network and Canadian Emissions Reduction Innovation Network, CAREN. it launches and holds numerous seminars, webinars, conferences, workshops, etc. per year. I thought maybe I should start first with the low TR level, technology readiness level of our research and development activities. So I thought maybe I should talk about the applied research work that we have done, which is about developing best management practices to reduce oil and gas sectors' methane emissions. So throughout the years, we launched and completed over 450 applied research environmental management projects, spending over $180 million. Over 40 of these projects are dedicated to methane detection in helping producers with best management practices, while policymakers and regulatory bodies can use the scientific and engineering facts for developing smart policies and regulations. All of this work is peer-reviewed, and so it has the respect of the public and academia. Through the PTAC's Alberta Upstream Petroleum Research Fund, we have developed several best management practices for reducing fugitive methane emissions from surface venting flow, casing, leak detection and repair, mitigation of low volume methane emissions, pneumatic vent gas measurement, etc., as you can see on this slide. This slide shows also a sample of applied research projects that we have completed, such as emissions reduction in dehydration facilities, establishing optimum spacing for enclosed combustors, understanding abnormal tank behaviors, which we'll talk about it later on, glycol dehydration, pump optimization, eco-efficiency handbook, and other activities. So the PTAC Fugitive Emissions Management Program Effectiveness Assessment, called FEMP-EA, is a world-class methane detection, quantification, and verification applied research project. FEMP-EA has sought to address the gap in understanding the efficacy of leak detection and repair LDAR surveys in addressing methane emissions. This work has created one of the largest comprehensive data set of bottom-up methane emissions at oil and gas facilities across Canada and the US. Preliminary analysis is expanding insight on the sources and components most prone to exhibiting high emissions. The study area is 2,500 square kilometers, 50 kilometer by 50 kilometer, was chosen based on the density and distribution of facilities in the Red Deer region. Approximately 180 sites, which essentially 180 large facilities, were surveyed at regular intervals between August of 2018 and August of 2019. This was done to find the optimum frequency of detecting emissions, so it would be an accurate and also effective way of reducing emissions. This program was on a voluntary basis, participated by 30 companies. The facilities producing from oil and gas reservoirs and range of various facilities in terms of size and single well and multi-well and well batteries. The Alberta Methane Field Challenge, Phase 1 and Phase 2 were field campaigns conducted in 2019 to assess the performance of new methane leak detection and quantification technologies at producing oil and gas facilities. 2 separate field trials were conducted in 2019, one in June and the other in November. Each of the field trials consisted of approximately 2 weeks of testing across 50 oil and gas producing sites near Rocky Mountain House in Alberta. The field trials tested 5 different types of leak detection methods: fixed, continuous monitoring systems, handheld devices, truck-mounted sensors, drone-mounted sensors, and aerial systems. Overall, 12 technologies were field tested as a part of this program. With Alberta Methane Field Challenge, we sought to understand the real-world performance of alternative methane leak detection technologies in comparison to conventional camera-based surveys. We developed methods to combine various technologies for finding most accurate and cost-effective approach to detecting methane emissions. The third ALT-FEM focus on methane emissions detection, attribution, and quantification of upstream oil and gas facilities, a comparison of two truck systems, and optical gas imaging. In addition to the technologies field tested through PTAC's program, 5 methane detection technologies developed, which are shown here. The first one is about methane detection using trucks and is like a technology readiness level of 6 to 8. Next one was LDAR SIM, was a flexible LDAR simulator to give us more information. And next one was intelligent methane monitoring and mitigation system. We use here the Monte Carlo statistical program to actually find the information that we were seeking and developing newer technologies and newer approach and combination of technologies that would give us the best information. Distributed Energy Efficiency Project is a technology that would track down not only the methane emissions in Canada, but also the cost and performance of each technologies. In addition, we've also done 12 technologies developed mainly using various sensors, drones, trucks, etc., as you can see here on this slide. One of the biggest challenges we are facing is still we are trying to find good solutions for it is methane emissions from oil tanks and condensate tanks because the emissions are very erratic. Our current focus is to find solutions, essentially maybe even using machine learning, etc., for this challenge. By solving this problem, I think essentially we can get very close to around 75 to 80% methane emissions target that we have achieving. Over the past 15 years, PTAC has secured funds from NRC IRAP programs, Alberta Innovates, NRCan, and Emissions Reduction Alberta to help SME develop their technologies. The methane mitigation technologies developed through PTAC collectively essentially is providing technologies around 37%. But one of these technologies that we have used and is already right now in place is called a REMView technology. So REMView technology captures light hydrocarbon from condensate tanks, from oil tanks, from mainly these days from compressors actually, and utilize it in the field for fuel. So this technology currently, the emissions is equal to taking 140,000 cars off the road annually, and also saving industry $15 million in energy cost. Having said that, the challenge of this technology is still the uptake of this technology is really low. And this is something I'm going to talk later on. In 2017, I thought it was about time to take a more systematic approach to addressing the value of that challenge. So I formed a consortium of field testing facilities, which is known as the Canadian Emission Reduction Innovation Consortium, or CAE. This consortium consists of 14 producers and 16 universities research centers. They are in Canada and in the US, as shown here, who have dedicated their lab and field testing facilities worth over $1 billion to CAE. In essence, what we have done, we have created an impressive network of testing facilities located from the East Coast to West Coast, as you can see from this map. By securing funds from Alberta Innovates and NRCan, and with industry support, we have been able to help the small and medium-sized enterprises field test their technologies at zero cost to them. So far, 3 technologies have been lab tested, 9 technologies have been field tested or developed, and 6 technologies are undergoing various tests. The methane mitigation technologies field tested through PTAC collectively have the capacity to reduce oil and gas sector's methane emissions by 48%. The list is provided here. Majority are essentially similar to technologies that we did to develop tests. So it's about chemical pumps, is about instrument air, which is essentially using compressed air rather than methane to run some of those devices. Is about combustors, is about electric dump valve actuator. This actuator technology, it came from military from the US, where when you add a small charge is an alloy that would contract and expand, and then so it can act as essentially running bunch of engines and pumps, etc. And there is this zero emissions also well sites, which we have done, and then again, numerous other technologies. Even if a technology is field tested, and I talked about it before, and proven to be cost effective and reduce methane emissions, SMEs still face the challenge of increasing the market uptake of that technology. To attempt to mitigate this challenge, we launched 2 consortia that pay up to 75% cost of equipment and installation, essentially encouraging Canadian producers to get a first-hand experience with the new technologies, so then they would do a mass deployment of these technologies, and then we would increase the market uptake of these technologies. These technologies aim to increase the investment in massive deployment of these technologies, and actually the results that we are getting, it seems it has been very successful. Methane mitigation technologies that they have been field tested and demonstrated are shown here. Again, many of them are some of the technologies that I have talked about. And what they do, essentially, they collectively increase the technology capacity by 39%. To further increase the market uptake of SMEs technologies, we also created a guide and directory listing over 59 Canadian cleantech companies looking to bring their methane technologies to international market. We are working with Canadian trade commissioners and with global affairs, etc., to promote these technologies. PTAC's product market fit assessment also helps cleantech SMEs prosper. Last year alone, we completed 55 assessments with the financial help from NRC IRAP and launched 20 consortia to help SMEs achieve economic prosperity. In the coming year, PTAC will launch several new initiatives to expand our international activities. This will include a strategic program to increase international sales of Canada's cleantech products and technologies. In closing, reducing methane emissions requires global collaboration. And it is through this collaboration that PTAC has achieved so much. So we really need to work with everybody to really get a good results on this achieving net zero. Thank you. And back to you, Eddie.
Well, thanks very much, Soheil. This is an impressive amount of work that's happened. Maybe because I went away, a lot of good things have happened, and congratulations on a really
it is
good
the other way around, Eddie. You actually essentially set the foundation for everything that has happened here. So I don't know how to
really
thank
impressive.
you. Yeah.
Really impressive, and thank you very much for your presentation. And any questions that are just to try to clarify some of the points that Soheil has made? That's a question to Anne-Marie or to Emmanuel. Let me just check the question and answer. Okay, we do have a question, and I'll reserve that question to be asked during the panel discussion because it more relates to the panel discussion. So from here, I'll move on to our second speaker, who is Dr. David Lezell, professor at the University of Calgary, and also heading the Transition Accelerator, which essentially is focused on the net zero energy system transition in Canada. David works with industry, governments, and academics to position Canada for the future in the low carbon transition. David, please go ahead with your presentation.
Thank you very much. I'm going to share my presentation and then we can get started. Thanks, Eddie. Much appreciated. And that was so impressive about what Soheil and the PTAC has been doing. And it fits very well to what I would argue we need to get to do in order to move forward in really making significant transition towards net zero energy systems. Now, I think as you know, everyone knows here is that Canada, United States, and dozens of other countries around the world have committed to net zero emissions by 2050. And in the Transition Accelerator, it's a nonprofit charitable organization that I helped to set up about 2.5 years ago. We've been focusing in the Transition Accelerator for how Canada can win in this transition and what are the best transition pathways. And if you actually look at our existing energy system today, which is shown in this chart on the bottom left, you can see that a lot of our emissions, matter of fact, more than 50% of them, are associated with the combustion of end-use energy carriers like natural gas, gasoline, diesel, jet fuel. So it's pretty clear if we're going to move to a net zero energy system, we've got to think about how we're going to change out these energy carriers to energy carriers that and fuels and energy carriers that actually don't produce emissions when they're consumed. Of course, there's also emissions associated with the production of those energy carriers, the upstream emissions, if you like, and they also have to be addressed. So I think there's a growing global consensus in what a net zero energy system looks like if we're actually going to really address climate change. And it shows a very significant increase in the role of electricity as an energy carrier to supply end-use demand, from perhaps more than a doubling of the contribution of electricity makes to our energy system. We also see perhaps an increase in the role of biomass that biomass maybe can make to end-use energy carriers, although there's some constraints there. And in fact, one of the things that's, there's a challenge because we're actually looking for our biological systems to help in the negative emissions to pull carbon out of the atmosphere and keep the carbon into a form that a solid form in soils or in vibrant ecosystems. But the one I really want to talk about today is this third one. It's a chemically based energy carrier hydrogen, which when combusted or when consumed does not release greenhouse gas emissions. And we've got to figure out how we're going to actually switch to those sorts of energy carriers as for providing energy use demand, and also how to produce them with minimal or no greenhouse gas emissions. So we might ask the question, why hydrogen? Why can't we just do everything on electricity? Well, the reality is that some sectors need chemical, not electrical energy carriers. Things like heavy duty transportation, heavy industry like steel making, et cetera, and space heating, especially in cold regions or in large buildings. So these sectors which are a significant proportion of the energy system, perhaps up to 25 or 30% of the overall energy system needs hydrogen. Then there's also, we need to, hydrogen also is not really in competition with electricity, but actually can complement the role of electricity as in more dominant role it's going to play in the future, because you can actually convert electricity to hydrogen and hydrogen back to electricity. And hydrogen can be kind of an energy storage molecule. And it's worth noting that when you have hydrogen, a low carbon hydrogen, it can be used to actually increase the biofuel production that you get from a given amount of biomass, and essentially preserve more biological carbon that's been pulled out of the atmosphere by plants, preserve more of that and make it into fuels. And that hydrogen plays a role in helping our biomass energy system. I think it's important to recognize that we already in Canada and around the world have a very vibrant hydrogen economy. And in Canada today, we make about 8,200 tons of hydrogen every day. And that hydrogen is involved with producing a greenhouse gas emission. It's called gray hydrogen. There's, for every ton of hydrogen going into the atmosphere, there's around 9 or 10 tons of CO2. And that hydrogen is used to make fertilizer for agriculture, to make fuels for transportation. It's used to crack bitumen into synthetic crude oil, or to convert various kinds of crude oils into gasoline, diesel, jet fuel, et cetera. And it's used to make other chemicals and materials. As we look to a net zero future, what we're looking at is it's changing the way that we make the hydrogen. We could still use fossil fuels or even use biomass, but instead of releasing the CO2 to the atmosphere, we can capture that CO2 and geologically sequester it or prevent it from going into the atmosphere. We can also make hydrogen from renewables or nuclear or other low carbon sources of electricity and use the electricity to crack water into oxygen and hydrogen. And there's also some hydrogen which is produced as byproducts of chemical process plants like chloralkyl or sodium hydroxide plants. And the vision is that in this new hydrogen economy, the hydrogen's not only used as an industrial feedstock, but used as a fuel in its own right, as an end-use fuel to support transportation, building, industry, and power generation, and even to be an export product for Canada, which is a significant opportunity. So let's look at what the value chains in this new hydrogen economy and how do we envisage this hydrogen economy looking by mid-century? Well, we talked about green hydrogen production here, where water is, low carbon electricity zero emission electricity is used to crack water into hydrogen and oxygen. There's also a possibility of blue hydrogen, biomass or natural gas or oil using through gasifiers or reformers to crack those into hydrogen and carbon dioxide. The carbon dioxide obviously has to be kept out of the atmosphere. So that's the first part of it. When we go up to the oxygen that's produced from the electrolyzer, most times today that oxygen is simply released to the atmosphere. But in a low carbon net zero energy system, that oxygen can be used to replace the oxygen in the atmosphere. And that allows us to then maybe continue to use natural gas, or other sorts of forms of fossil fuels. But because the gas that's produced as an end result of this contains no nitrogen, because you're not using atmospheric nitrogen, it contains virtually pure CO2 or CO2 and water. You can remove the water relatively easily and get virtually a pure CO2 stream that can be sequestered geologically. And this can allow us to run cement plants or even power production on fossil fuels with pure oxygen. And there's an opportunity that opens up with lots of green hydrogen production. The hydrogen could be used, and this is some of the early stages of hydrogen use in energy systems, often in Europe and also starting in Canada, where the hydrogen can be blended into natural gas and to help to start to decarbonize our existing systems, for example, residential or commercial buildings, or even to help to start to decarbonize power generation. Then, blendings of up to 20% by volume, which is only about 7% or so by energy content. Blendings of that range, you don't typically need to change much infrastructure here. You can use the existing infrastructure. But obviously, that's not going to get us to a net zero energy system. What is being looked at a lot in Canada and internationally is the possibility of putting pure hydrogen in to space heating for residential commercial buildings, or even pure hydrogen for power generation. That will require some new equipment, new burners or new boilers, furnaces, cook stoves in houses, or gas turbines for power generation. The area where hydrogen is often seen as having the biggest opportunity in terms of a very significant opportunity is in the area of transportation, especially heavy vehicle transportation. In which case, hydrogen can be taken from a pipeline, that hydrogen pipeline, and be delivered to a fueling station, or the hydrogen can be compressed into a tube truck, and each tube truck can maybe hold perhaps up to 1,000 kilograms or 1 ton of hydrogen, which isn't very much actually, but it's which makes the tube truck rather an expensive way to move hydrogen around. Or the hydrogen can be reduced in its temperature to about 253 degrees Celsius below zero, and it turns into a liquid. And the hydrogen then can be put onto a truck as liquid hydrogen in a cryogenic container and delivered to the fueling station. And of course, the opportunity here is to use that hydrogen to support heavy vehicles in particular, everything from airplanes and trains and ships, off-road vehicles, a lot of Class 8 trucks and bigger vehicles that are used a lot, municipal buses, etc. There is a role perhaps for cars, but it's probably only not for personally owned vehicles, but for fleets of vehicles that are used very heavily and under long distances. And we'll talk more a bit about some of these alternatives. Then the other part of the hydrogen economy that there's a lot of interest in Canada and internationally is the possibility of using hydrogen as an energy carrier for export. And this could either be done as exporting liquid hydrogen production, perhaps by train to tidewaters where it puts on a ship, or one that is really getting a lot of attention in the last couple of years is converting the hydrogen to ammonia. Traditionally, that's thought of as a fertilizer. But hydrogen and ammonia is a lot of energy embedded in those molecules, and that can be taken to supplied for export markets. And indeed, Japan has made it very clear they want to import millions of tons of ammonia per year as an energy carrier. And that could either be produced and taken by train, or perhaps a pipeline that would be ammonia be produced at the coast. And of course, there's a possibility of pipelines delivering hydrogen to other jurisdictions in North America, et cetera, from Canadian sources. So Canada has an opportunity because we're amongst the world's internationally recognized as amongst the world's lowest cost producers of both blue hydrogen, that's made from carbon-based sources, and green from electrolysis. And as you can see on this chart, which is from about 3 years ago, Canada is recognized from when you make hydrogen from natural gas with CCS, in provinces like Alberta, British Columbia, and Saskatchewan, it's possible to get prices of hydrogen which are about half the wholesale cost of diesel and 1/3 the retail cost of diesel. This opens up a very interesting opportunity for the production of these fuels that actually start to feed into the diesel market. And this has been something that's been a lot of interest that we've been looking at within the Transition Accelerator. So Canada has a low-cost blue and green hydrogen, but what about its environmental footprint? And the analysis is that in the process of making hydrogen with carbon capture and storage and using a process like autothermal reforming to make the hydrogen and then capturing the CO2 and sequestering it, that drops the carbon intensity of the hydrogen down to about 0.5 or 1 kilogram of CO2 equivalent for every kilogram of hydrogen. But then you have to add on the upstream emissions, basically the methane emissions that Soheil just talked about. And in our estimate, that adds another 2 kilograms of CO2 per kilogram of hydrogen for a total of 3 kilograms of CO2 per kilogram of hydrogen. And that's the best we can really get to today. And what we're really looking at is for the work that Soheil is doing to actually be implemented and see very significant reductions, 75 to 90% reductions in methane emissions upstream. And this, the carbon intensity of blue hydrogen will drop to below 1, we hope, kilograms of CO2, and be right in the range as the very best of the life cycle emissions associated with green hydrogen production. And so, but whether we're taking blue or green today, we can achieve when it's actually goes in to replace diesel fuel, for example, in transportation, or heating fuels that were used for building and industry. You see reductions, life cycle reductions of 80 to 95% for transportation, maybe 67 to 90% for heating fuels. And this is well on the pathway, on the transition pathway to net zero. So we see this as a really important part of that transition pathway. So what markets for hydrogen are most promising? Well, I think it's pretty clear that heavy transportation offers a market where hydrogen is most likely to be economically viable. We can make blue hydrogen in this range around here, say $1.50 to $2 a kilogram, which actually has an energy content equivalent to a lower end of wholesale, or even sometimes at half the wholesale cost of diesel fuel, and a third of the retail cost, as mentioned before. It's more difficult today for green hydrogen to hit that target market without subsidies, but the cost of green hydrogen production is coming down with lower cost of electrolyzers and lower cost of solar and wind in strategic locations. When you have the right conditions, and when you couple solar and wind to electrolytic hydrogen, green hydrogen should be able to get down around the $2 a kilogram range by 2030 in certain regions. What's more challenging is the space and water heating and industrial heating, because they're used to very low cost for hydrogen, and it's a very low cost for natural gas on an energy basis. But even when you look at those sectors, when you look at the alternatives of switching those sectors to electricity, for example, or other challenges at a system level, hydrogen often comes out as likely the best net zero choice for many of those sectors. Not all of them, but many of them. And I think we're going to see that the synergy of hydrogen being used for transportation fuel, but also being used as a heating fuel, there's an opportunity for a coordination of the infrastructure deployment in the next 10 to 20 years that will really help to address both of these challenges in these difficult to decarbonize sectors. So then we could ask, we've looked at the wholesale cost of making the hydrogen, but what's really important with hydrogen is, especially when you look at it for transportation, is the cost of actually preparing and delivering that hydrogen to a fueling station and the cost of the fueling station. And this chart shows 3 different sizes of fueling stations, 0.4, 2, and 8 tons of hydrogen per day. And it shows that the lowest cost for the 0.4 ton a day, these are all within close to a supply, but is tube trailer, liquid hydrogen, and pipeline alternatives. So the point I want to make on this chart is that, first of all, the fueling station size has a major impact on the retail cost of the delivered hydrogen. And so to be economically sustainable, our analysis is a minimum of at least 2 tons of hydrogen per day is needed before you can even get close to being in the range where it's possible that the cost of hydrogen can be an energy equivalent cost of diesel on an energy basis. And so that requires, to put that in perspective, a 2 ton of hydrogen per day requires about 80 hydrogen fuel cell electric buses for every station that are fueling essentially every day, or perhaps 40 Class 8 trucks. These are big transport tractor trailer trucks that are carrying 40 to 60 tons gross vehicle weight, and those refueling at the station basically every day. The second point here is that, well, hydrogen production cost is important, and the hydrogen production cost is shown in blue here based on the previous analysis. It's about $1.60 here per liter or per kilogram. The cost of the other parts of the value chain are of equal or more importance. Preparation and delivery, highly variable depending on whether you're doing tube trailer, liquid hydrogen, or pipeline, and also the cost of building the fueling station itself. Whether it's, and it costs a lot more to build on a tube trailer than on liquid hydrogen on the same basis. But, liquid hydrogen the fueling station cost is lower because the compression can be handled a lot with the liquid hydrogen as you gasify. And pipeline can be some of the lowest cost, but it depends a lot on where you are and the size and the size of the station and what other demands are in the region for hydrogen. So I think this is really important to understand that the choices that are going to be made are going to depend very much on region and locality. So how do we take this information and build a new hydrogen economy? We're essentially talking about creating a new value chain. Well, I think the reality is we've got to really come to grips with the fact, I've already alluded to this, that as a gas, hydrogen is more difficult to move around and store than liquids, especially in small quantities. So what we need to do is we need to bring together low-cost waste, blue and green hydrogen. We have to find substantial markets nearby and especially transportation markets, but also possibly some heating fuel markets. And we got to combine the two at a scale of supply and demand where the economic works without sustained public investment. Certainly, there's strong evidence we're going to need public investment to get this new value chain started, but it has to be very strategically placed in order to be able to ensure that we're not creating a system that's going to require ongoing continued public investment. We have to get it to be self-sustaining. And that's going to require an engagement of industry, governments, and academics. So what we're looking at within Alberta is actually piggybacking this system on our low-cost industrial blue hydrogen production that is already starting to occur already. To pipeline that, ideally pipeline it nearby, but also there are other routes. We can also take it by liquid hydrogen, but initially pipelining it to nearby markets, rapidly growing the demand, whether it's in trains, buses, or trucks, or maybe some space and heating for residential and commercial buildings, or even for power generation. And this pipeline could also provide an opportunity for green hydrogen to find access to market. There's certainly a role for liquid hydrogen, especially in the early stages of growing this out, but it adds about $2.50 to $3 a kilogram to the price, which makes the economics a little more challenging. But so this is the approach we've been using. And in Alberta, Alberta is already a major center. We talked about Canada producing 8,200 tons of hydrogen. 2/3 of that is produced in Alberta for use as I talked about, as industrial feedstock. Within the Edmonton region of Alberta, we've already have a lot of the infrastructure. It's been built over the last 20 or so years. There's a 50-kilometer long hydrogen pipeline and 2 CO2 pipelines. The Quest CO2 pipeline goes to Salem aquifer storage, and Alberta carbon trunk line is used for enhanced oil recovery. And if you look at this region itself is about 2,000 or 2,200 tons of hydrogen per day, a little more even. And some of it, there are 3 plants up here that are actually already making a form of blue hydrogen where they're capturing the CO2 and putting it into these pipelines that we show in here. And indeed, in the last 6 months, we've seen a number of announcements where both some of this in the Alberta Industrial Heartlands, other places in Alberta, where there's major announcement of blue hydrogen production initiatives or initiatives related to it. Suncor and ATCO are talking about major blue hydrogen production. That'll be later this decade. Air Products is talking one and only about 3 years from now. They'll be having their 800 tons a day or 900 tons a day of hydrogen being produced. Scotford has said they're going to make their CO2 infrastructure available around the resources available for companies to store their CO2. And then there's 3 companies that have announced major blue hydrogen production converting it to ammonia, and then exporting the ammonia from Canada or using the ammonia as an energy carrier in other places. And so there's been literally more than $5 billion worth of various announcements in the last few months. And so what we've been interested in is what are the demand markets. So a lot of companies are out there talking about supply, but where could we use that and start to grow a sustainable hydrogen economy in the region? This is the close-up of Edmonton, showing the, I don't know what happened, my screen just went out, so we will bring it back. There we go. Edmonton showing the, the region around Edmonton where we have, get it back again, yes, where we have the red dots are the private trucking fleets. The fueling, the little fueling stations are the private truck fueling stations, and there's a number of these. The blue icons here are municipal vehicle fleets, either bus fleets or garbage trucks up in this region, or snow plows and that sort of thing. And we also see here the green X's are the gates where high pressure natural gas is dropped to low pressure, and we see the ability to then inject hydrogen into natural gas systems for space heating for commercial and residential buildings. And what I want you to note here is they're on two corridors. These happen to be the industrial corridors through the city. And this opens up a really interesting opportunity to put pipeline infrastructure. And indeed, there are a number of, in this corridor in particular, in the one coming down into the south part of the city, there are a number of abandoned or discontinued pipelines that could actually possibly be retrofitted for hydrogen movement. Overall, the market, we've estimated a market potential in Edmonton alone, just in this region, of about 670 tons of hydrogen per day for transportation. That's mostly the diesel market, a little bit of a gasoline market. And building heating could be another 1,500 tons a day to support, the space heating if we went to 100% hydrogen, plus export markets of many thousands of tons per day of potential export markets. So let's just now talk a bit about some of the issues around this new value chain, and where is the power and control in this value chain, and how does it compare maybe to some of our existing value chain for heavy transport in this sector. What I really want to focus on, the thing I really want to focus on here is the two red dots here, but especially the heavy duty vehicle buyers and users. These, we would argue, are the key stakeholders. If you think about it, they will eventually pay for this whole value chain. When they buy a vehicle, they're paying for the vehicle, they're paying these companies here, the OEMs, and they're going to be using that vehicle to deliver a service, but they have to buy fuel, so they're going to be paying for all of this upstream system here. So it's very important that we're developing a new energy system that they need to be engaged in this process, and their interest needs to be addressed from the very beginning if we're going to move forward on this. And of course, this is a challenging because this sector happens to be highly competitive, and they don't tend to work collectively as much as perhaps some other sectors. And they're smaller companies that literally 17,000 companies in Alberta alone in that sector for the heavy vehicle transport. The OEMs and the retrofits, now these tend to be global companies. And we are competing, and some of Canada is competing for their attention to build vehicles that will actually meet the needs of our markets. And when our markets, when you consider the weather we have, especially in Alberta with the snow and sleet and everything else, it's much more attractive for them to focus their attention on places like Arizona or California than Alberta. But the reality is that when we talk to them, the most important thing that they're looking for is that the key stakeholders want to buy their vehicles, and that will get them to work with us. The third part I want to note here is the actual fuel delivery and retail. In our existing energy system, if you look at the value chain and who makes the most profit in that value chain, it's this sector that actually is a major profit center. This and the upstream and the production of the fuel. And so, but for the key stakeholders to really drive this transition, we're wanting the key stakeholders to accept the new fuel and start to move to these new net zero fuels. They're going to have some confidence in the future of fuel pricing, especially when initially there's going to be monopoly status. The companies that are providing a fueling station, there's only going to be one fueling station. They're going to have a monopoly over the hydrogen sales. So public funding in this sector, we argue, must ensure that key stakeholder needs are met. And then finally on the fuel supply, the reality is, as you can see from my previous things I've noted, is that the companies that are making hydrogen and can make blue hydrogen and green hydrogen there's a lot of them out there who see the possible economic opportunities in this new value chain, and they're very keen. And I would argue that we also need to be thinking about public subsidies. They're also asking for public subsidies, but they need to be tied to, again, some level of confidence in the prices of the fuel, at least until a competitive economy exists in this area. So one of the things that we've been doing in the Edmonton Regional Hydrogen Hub, which has been set up around the fact that we've got this incredible opportunity in the Edmonton region, is a number of projects that I'll mention very briefly before I wrap up. First is AZTEC. We're designing and building two 63.5-ton gross vehicle weight. These are very large trucks. And they're going to be running the Edmonton and Calgary route. They're being designed by Dana Transport and Ballard, and with a project run by the Alberta Motor Transport Association, and the estimated time of arrival will be January, about a year from now, year or 14 months from now, when they'll be on the roads. There is the AZIT project. This is a zero emission hydrogen transit involving Edmonton Transit, Strathcona, Calgary, and Rome. But Edmonton and Strathcona in particular, two hydrogen fuel cell electric buses. We just received the funding for this, and those buses will be on the road in August 2022. CP Rail has announced some really exciting work that they're doing. They're putting 3 diesel electric locomotives on the rail. The first one will be on the road in 2020, on the rails, not on the road. I hope on the road, but on the rails in 2022. Then we're looking at a number of companies and a number of projects on hydrogen diesel dual fuel technologies, where hydrogen is injected into the diesel engine and it improves the combustion of the diesel fuel. But what it really does is it replaces about 30 to 40% of the diesel fuel requirement. And we see this as a really important bridge technology for creating fueling station demand and building out the fueling station network while also reducing emissions. We don't see it, we see fuel cell vehicles as a long-term solution, but this is an interim solution, which in our models are really important in keeping the need for public subsidies down and really deploying rapidly a hydrogen economy in the next few years. We're also working with the Alberta Motor Transport Association to run a roadshow where we're taking hydrogen diesel dual fuel vehicles and fuel cell electric vehicles that are commercially be coming out in the next year or two in North America, and providing carriers hand-on experience. And we just received some funding to get this off the ground. We hope to see a lot more. We've been working with a number of companies about the concept of providing the fueling stations, and Suncor in particular. We're able to, it's been announced recently that we've got some funding. The first fueling station will be going in the next few months to serve some of the projects I've just talked about. And we're hoping to see a major expansion in that area. There's also a number of projects that have been launched in Alberta, and I've just mentioned 2 of them I think are quite important. One is looking at actually making hydrogen directly from natural gas without the steam methane reforming or autothermal reforming, doing it by methane pyrolysis, where you produce carbon black instead of CO2. And the carbon black then is obviously can either be converted into rubber tires or paints, or basically make something else with the carbon black. It's just keep it out of the atmosphere as CO2. And ATCO is looking at blending 5% hydrogen into its Fort Saskatchewan infrastructure for space heating in Fort Saskatchewan. So what is the magnitude of the opportunity? Very briefly, I would like to touch on 4 things just to give you a sense. They're all focused on Alberta. I'm sorry, I know this is more about pan-Canadian, but this gives you a sense of the scale of the opportunity. Alberta uses a lot of diesel fuel. Over almost 280 petajoules of diesel per year is shown here. If 80% of that went to hydrogen, and hydrogen in a hydrogen fuel cell electric has a drivetrain efficiency of a joule of hydrogen will take a vehicle further than a joule of diesel fuel. There would be about 195 petajoules demand. when you add some from the gasoline, maybe 220. This would require production by 2050 of an additional 4,200 tons of hydrogen per day, which is about a 79% increase in the current Alberta hydrogen production of about 5,400 tons a day. And that would require, that would have a CCS, carbon capture and storage, about 13 million tons of CO2 per year, over 400 fueling stations at 10 tons a day. These should be highly economically viable. Some fueling stations would be larger than that, of course. Natural gas decarbonization is also a possibility. And we can look at, this is the amount of natural gas that's produced in Alberta in a year. It's over 4,000 petajoules of natural gas per year. A lot of it's used in industrial processes in the province. Residential, commercial heating are shown here. We're saying, well, maybe about, a little less than half of it, say 1,000 petajoules, start with blending, and then we'll go to pure hydrogen. That would be 1,000 petajoules. That's 19,000 tons of hydrogen a day, a 358% increase in hydrogen production, 60 megatons of CO2 sequestration that would be required. If we could look at the hydrogen or the natural gas we now export mostly to the United States or to other provinces, this is exported to other jurisdictions. And we're saying, well, if 80% of that, if say they didn't want our natural gas anymore, but they wanted hydrogen, that would be, at 1,340 petajoules per day, it's 26,000 tons of hydrogen per day, another 81 megatons of CO2. Now, green hydrogens could also play a role in this, but to put it in perspective of the scale, green hydrogen production if you wanted to make it from wind, to make the 26,000 tons would be 147 gigawatts of new wind generation would be needed, which is 87 times the current wind generation capacity in Alberta. It's 25,000, almost 6 megawatt wind turbines. So there is a market, I think eventually, where it's going to be a market for both green and blue hydrogen. I think blue is more likely because of its cost benefits and the ability to get to scale quickly, are more likely to build out some of the infrastructure, opening up the opportunity for more and more green as we go on. And then finally, the moving hydrogen to Asia. I talked before about the two interests, either moving it as liquid hydrogen or as an ammonia. There's also a liquid organic hydrogen carriers that's possible. But moving it, the hydrogen, there's different ways of getting it across. Market demand already is over 8,000 tons of hydrogen per day in Japan by 2030. So we're talking very significant opportunities and economic opportunities. A lot of companies interested in taking and moving on this opportunity. So in conclusion, many nations of the world, including Canada, are committed to this transition to net zero energy system. Canada's poised to lead in this transition because we've got really low cost blue and green hydrogen, and we need to focus on these hubs and corridors to build out demand. And I would argue we need to start right now. Thank you.
David, that was an excellent presentation. You have provided us with exciting ideas, possibility, new pathways to create, I think, a new industry. And you've described potentially huge opportunities as we move forward with hydrogen as a part of the value chain. So thank you very, very much. That's excellent. The two of you have done a masterful job, and we are now ready to move into a panel discussion. And I invite each of you to ask each other some questions. And as a moderator, I was hoping to be the first to ask questions, but since we've got some excellent questions that have come, I will start with Soheil and move on to you, David, as we move along. And if there's time, I do have some questions that I wanted to ask as well. But let's start the show with a question about for Soheil, which talks about your presentation, meaning Soheil's presentation, focused on operating facilities. What is known about fugitive emission from shutdown and abandoned wells, the wells that have been abandoned or shut down?
Well, that's an excellent question because as you probably know, when we are talking about shutting facilities, In Alberta alone and in Canada, we have few 100,000 wells. And many of them are abandoned or shut in currently. And the challenge with them is that when we are essentially drilling these wells and doing a cement job behind the casing, unfortunately, cement would shrink and so would create microfractures. And these microfractures could be a place where methane would be emitted. They estimate, this was a Schlumberger estimate, I think 10% of wells when they drilled, they have that problem from the beginning. But something that was even more concerning was that during the, over the history of these wells, almost 50% of them would create that microfracture. So the issue is how much are we venting and what have we done to overcome that challenge. We have done actually measurements in terms of these wells, and the wells that they are right now leaking, essentially an average well would leak as much as a cow, generate greenhouse gas emissions. So that's kind of a perspective in terms of the size. Is relatively, well, you can say is either a small or maybe cow is too much, but I'm not going to comment about that. But so what have we done? We have actually gone through numerous technologies trying to address this challenge. First, there were a bunch of projects that we are doing that is using a ring that expands when we set it, and then we put some even maybe heavy oil or bitumen material on top of it, which creates a seal. The second thing that we have done with respect to these actions, we have several projects ongoing, and we are doing the lab and field tests, are changing, adding additive materials, various materials. Some of them are nanotechnology, nanomaterial, to cement to create a better job, and then so be able to stop the leak. But the bottom line is there's a significant amount of work is going on the shutting aspect of oil and gas in terms of generating methane emissions and trying to solve those problems.
Okay, thank you, Soheil. The next question for David is, can existing natural gas pipeline infrastructure be easily converted to hydrogen transmission use?
Well, I think so. There's different kinds of pipelines. Obviously, for distribution pipelines, for example, from low pressure pipelines going to people's homes, from most of that in Canada, much of it is plastic or maybe cast iron, and that can be converted fairly easily. It's not really a problem. You don't have an embrittlement problem with cast iron, and plastic pipelines work well as well. Some of the valves and fittings have to be changed, perhaps, if you go to pure hydrogen. But if you want to bleed in hydrogen up to 20%, you don't need to change that infrastructure. When you get to larger transmission pipelines, then, especially some of them can take hydrogen, and there's some companies that people want to contact me, I can send them links to companies that are sort of mapping out which ones are ready to go and which ones need some modifications. But a lot of them will need modifications, because if there's sort of a high carbon steels, the hydrogen can get in there and actually pull the carbon out and cause embrittlement in the pipeline. And so there's quite a bit of work being done now as to how to retrofit some perhaps disused pipelines by putting a plastic liner down it, or putting a pig down that actually coats the pipeline with material that protects it from hydrogen. And I think we're going to see quite a lot of work in being done in that, and some demonstrations going in the next few years. But some of it, there is a possibility to just put a liner down, plastic liner or something, and then it becomes a pipeline with lower capacity, obviously, then because you've got a new insert in it. So, but I think it's a great question. It's something that so you've done work in this space, I think so. Or you're so what do you think?
No, you did an outstanding job answering the questions. I think just I want to mention also there is this potential that we can have up to maybe 15% hydrogen in moving with natural gas essentially, and so that would be one way of actually transporting hydrogen. And as you mentioned, I think the fiber reinforced polymer and some of the pipes potentially made of polymeric composites and engineered plastics. I think these are the ones that I think people are right now looking in terms of technology.
Okay, thanks, David and Soheil. The next question is for Soheil. Great presentation. 75% reduction versus 2012. How does this compare to 30% versus 2005 production?
So I gotta confess, I really don't recall what the 2005 methane emissions is, but here, these are my thoughts. And definitely 2005, we had much higher emissions. Number one, because we weren't using good practices as what we are using now, but also our production of oil was, conventional oil was much higher. So what I can say about Canada's methane emissions performance is that we produce around 17 BCF per day of natural gas. And the amount of our methane emissions is 0.16. So essentially less than 1% of methane that we produce, we are emitting. Globally, the rest of the world produces 383 BCF per day, and their methane emissions is 10.84 BCF for 3%. The 3% is what, Eddie, you mentioned that actually can get us to have worse than, I would say, worse than coal. So the bottom line is Canada is doing an outstanding job when it comes to methane emissions. Even the aerial photograph that I showed that we are #5 producers, but many of countries that are producing significantly below us, they are producing more methane.
Okay. Thanks very much, Soheil. This is a question for David this time. Where does hydrogen fuel cell vehicles stand compared to electric vehicles in heavy duty transportation? And the second part of this is who are going to bear the vast investments required to establish hydrogen production, distribution, and storage infrastructure, the infrastructure?
I think they're great questions. So in terms of electric vehicles, I think there are some, we've heard about Tesla's truck, that electric truck. There are a few trucks, especially in Europe, that are smaller class 8 trucks or class 3, 4, 5, 6, 7 trucks that are electric. And they make sense if you're not driving very much in a day. So perhaps you're going to be putting on 100 or maybe 150, 200 kilometers in a day, or your load's not too great, because then you can, you may be only carrying 20 tons or something. Then those trucks are probably best to just be electric. And especially if you're not driving very much, because they're parked overnight in a return to base location, you could set up infrastructure and start charging them at night and have them ready for every day. And indeed, in our analysis, we in our models that we develop, we go in and look at fleets of companies and identify, these ones should just be electric. These ones maybe should be hydrogen electric. Where you need hydrogen electric is when you get to the larger vehicles that are longer distance transportation, where if you actually had to put batteries on to do it, You'd have the batteries would very seriously limit the load. You'd have to have one trailer, which is just batteries, right? And then your charging of the vehicles becomes really problematic because it takes so many hours to charge a vehicle, whereas to refuel a hydrogen fueling tank is 10 minutes or 15 minutes, something like that. It's so closer to what a diesel vehicle. And I think especially as we look forward in the next 5 or 10 years to the deployment of autonomous vehicles, especially in the trucking sector, because these autonomous vehicles, they won't even be limited by, right now, a lot of our use of our heavy duty vehicles for transportation are limited by having drivers. Drivers can only work for 12 hours a day, blah, blah, blah. And so when we move to autonomous trucking, they're going to be running 23 hours a day and they're back and forth and you're going to be on the road all the time. There is no time to charge. So it's a fit for service issue. And when we talk, we work very closely with the trucking companies to what their needs are. And they're very interested in zero emission alternatives. And it's very clear that for those that run the big vehicles, long routes, really heavy loads, it's basically electric vehicles won't work. Now, the second part of that question, which it seems to have disappeared from the list here, so I don't see it, but maybe that's in the previous one. I'll see if I can find the question. Yeah, who's going to bear the investment? What we are doing is, the reality is that if we can get to scale quickly, our analysis is, yes, there will be some public investment required. My feeling is we should be taking the carbon taxes that people pay on their diesel fuel and redirect that to create this new value chain. And but once the value chain is set up, it pays for itself, and especially when the place for the fuel supply, et cetera, because we can actually we pay a lot for our transportation fuels, and compared to diesel, especially diesel plus carbon taxes, I think we can once it gets started, it will get a life of its own, and it's not going to be as onerous an economic investment as what it might seem at the start. But certainly there will be some. Putting it into space heating is more challenging. And I think that we are going to need a conversation in Canada. We've been looking quite a lot at how Canada is going to deal with being a cold country with its space heating loads, replacing natural gas. And natural gas is pretty hard to replace. We've got all the infrastructure. We're going to be having to spend more for space heating in the future, I think, and maybe it'll get us to insulate our houses better. And I think that would be a good way to, we should be building to much higher building standards for new buildings, and we should be thinking really about trying to retrofit our existing building structure, because the energy cost for space heating in 20 years from now, I think is going to be more expensive than what it is today.
I think that's a good prediction.
That's right.
Well, this is a question I think that both of you can take on. Have estimates been made of how much CO2 can ultimately be permanently stored in Alberta in our depleted oil fields? How does this compare to Canada's annual fossil fuel GHG emissions today? So if you take all of our emissions today, how many years do we have of potential storage?
Well, maybe
Soheil, do you want to go first?
Yeah, so you go first.
No, go ahead.
Okay, well, maybe I can say that we are sequestering today about 2.5 million tons, or maybe 2.5 to 3 million tons per year today. In the hydrogen economy that we've modeled, we're saying, we may need to take that to 100 million tons or even 200 million tons a year if we have a full-out blue hydrogen. Now, how much of our hydrogen will be produced from carbon-based sources require CCS, and how much would be produced from green hydrogen, say wind, solar, nuclear, where hydrogen, but it's a good question. We don't need the CO2 sequestration with that. And how much might be produced from methane pyrolysis, where we take methane, they make the hydrogen for the methane, but you're burning solid carbon, in which case we don't, we could landfill that if we had to, and just prevent it from decomposing. So I think that what the number really is in the hundreds, is probably the tens to 100 million tons of CO2 per year. Our analysis, when we look at the work that's been done on CCS in the last 15 years, suggests that that kind of space may well be available, but it's not been fully documented. And I would argue more research is needed. And certainly we got many tens of millions of tons capacity. We could identify even, pockets. We have a report coming out in January that will try to identify some early places. But so I'd be interested in Soheil's assessment of, what's needed in the research and the technology development to open up, to really understand how much capacity we actually have.
I think you're absolutely right. The capacity for storage, especially in Alberta and mainly in Alberta heartland, golden trend, where we have huge depletions from 7 or 8 major fields. And there's a huge actually aquifer there. There's huge capacity there. There's no question about the capacity. It's more like about the cost, because majority of our CO2 generation is right now is from oil sands area. And there is around 400 kilometers or more pipeline required to take those CO2 into these major reservoirs. And the cost is gonna be extremely high. I mean, people are talking about $175 per ton of CO2 cost. So that's where the challenge is really extremely high cost for injection. With respect to hydrogen, of course, that would be a different story, because there are lots of low-hanging fruit in terms of finding places where you would generate hydrogen and then you would inject CO2 into nearby reservoirs. And that would be, again, Alberta heartland.
Yeah, I think from my memory, there's something like 300 years of storage capacity at today's values. That's going back a few years from studies that were done by people like Bill Gunter and Stefan Baciu.
Yeah.
Turning now to David. This is about the 20% hydrogen blend, but we know that there are, the ATCO pilot is really about 5%. How do you get to much higher dedicated hydrogen pipelines, or a systematic replacement of natural gas pipeline components and consumer equipment to make it all hydrogen friendly?
No, I think that's a great question. Well, I think it'll start, well, first thing that has to happen is we've got to have some policy changes in Alberta that allows hydrogen to be put into natural gas pipelines in more than just a pilot, right? It has to be, and those, the recent Alberta hydrogen strategy or hydrogen roadmap that just came out committed that the government will be trying to make those policy regulatory changes in the next year or so. So hopefully that will happen. That will allow even the, the 5% and to be put into natural gas mixes and start to decarbonize a little bit. When going to 5%, 10%, 15%, even 20%, there probably doesn't really require any end use changes. It'll be increased slowly to that. Above 20%, 15 to 20% work done in the EU and in the UK suggests that after that, you start getting changes in the way the flame burns, and you have to start changing orifice size, and you have to start changing some other technical details about your burning, and that's going to require typically a step change where what they're doing in the UK now is they're basically identifying one part of a city, for example, a subdivision, and they're saying the whole thing will switch to 100% hydrogen. And what they would do is during the summer, they would basically turn off the natural gas system. They would go into everybody's house. They would have, spent the year before figuring out all the burner tips and what furnaces have to be replaced and what cook stoves need to be replaced. And there would have to be a major switchover. Whether that, how that happens, it's been done before in the UK. UK, we used to be on coal gas. They went to natural gas. Coal gas was 50% hydrogen. They went to natural gas back in the 60s and 70s or whatever, and they did this sequentially. They're now talking about doing it again in the UK. And we've been in conversations with the organizations that are planning this, saying, okay, what would be involved in doing this in Canada, right? And obviously it would be done over the summer. So by the fall, you would be, one winter you would be on heating for natural gas, or maybe a natural gas hydrogen mix, and the next year you'd be on pure hydrogen. My sense is that it's going to be new subdivisions. We hope within 2 or 3 years from now, we'll be looking at some subdivisions in Alberta, which will be 100% hydrogen as some trials, and try to get the manufacturers. There's no reason we can't do it. It's just a matter of getting the planning really well staged. But it is going to require, this is a game. This is a major, if we're going to talk about major infrastructure changes, this is the bigger challenge, is on space heating.
David, this is also a question for you. Can you comment on safety issues related to hydrogen and also safety in hydrogen storage and transportation?
Well, I think hydrogen as a transportation fuel is probably safer than gasoline and diesel. If you have an accident and you have spill of gasoline or diesel, we've seen this, it's where the fuel goes underneath the car, catches on fire, and this becomes a roasting pot in the vehicle. A hydrogen tank leak, it's going to be like a torch, because these are compressed gas tanks. So I think that and then you think about whether the fueling at the fueling station, where you're actually putting hydrogen into a vehicle, that will be putting a knob into your vehicle and locking it, sealing it, right? If you think about it, if somebody came out today and said they had this liquid fuel and they wanted to have fuel a vehicle, and you were going to be able to go to a pump and pull a lever off a pump and squeeze the handle, and the explosive flammable fluid would squirt out, you would never be allowed today. The fact is it was allowed. It was allowed in 1910, right? And we basically haven't changed the system. But the new system for hydrogen is going to be so much safer than somebody sitting there smoking and filling their car with gas. So I think the hydrogen system is going to be safer. We know how to handle explosive and dangerous chemicals. I think that I don't think the safety is a problem. We just have to do it properly. I think it's probably safer than our existing energy system we have today. In terms of storage, the best storage for hydrogen is large terms, industrial, is salt caverns, and lowest cost. And there's quite a lot of interest and work being done in Alberta now on trying to identify salt caverns that could be used for large scale hydrogen storage to give you that seasonal buffer, for example. In terms of right now, storage tanks at a fueling station have to be above ground. There's a bunch of regulatory processes about the possibility of being able to bury hydrogen storage tanks. And I think a big issue here is, how are we going to be storing it? There is a major technology breakthrough that could come in the next 2 or 3 years that would change a lot of what our energy system looks like. Ballard has just partnered with Chart Industries to basically put on board liquid hydrogen storage on board a vehicle, so that what you would have on vehicles, whether it's big trucks or buses or airplanes, or like in the rocket ships in NASA, you would actually store liquid hydrogen on the vehicle, and then you pump the liquid hydrogen out and only gasify it when you need it. Now, for big vehicles that use a lot of fuel, this makes a lot of sense, and it also reduces dramatically the size of the chamber that you're using, and means that you could put enough fuel on a vehicle to say take it 1,000 or 2,000 kilometers. And that, if that breakthrough comes, and there are companies all around the world working on it, our fueling stations would be liquid hydrogen fueling stations for heavy trucks. They'd have probably a compressed gas component as well, but liquid hydrogen would play a more important role in that vision for the future. And that, obviously there's these are very they can't be totally sealed containers because the liquid hydrogen is constantly boiling off and you're taking that off. So there would be, I think that we would be seeing a change in what our hydrogen economy might look like, if that technology is deployed in the next few years. And there are a number of companies working on it.
There's also, with respect to green hydrogen, this opportunity of storing it in these huge balloons under the dam.
Yeah, that's interesting.
Interesting. Well, thanks, David and Soheil. Next question is for Soheil from me. And it relates to COP26, which just finished this month, where we had more than 100 countries agreeing to slash methane emissions. It's a non-binding agreement. So the question for you, is it a powerful signal for the future, or is it much ado about nothing?
Well, if there's collaboration, if the world is serious about it, if they all come together, the technologies are there, we can make it happen. I hope that they are going to take it seriously, but there are many countries, they really, to be honest with you, when you look at the performance and what they are doing, they have not paid attention. We in Canada are doing a great job in terms of reducing methane emissions, developing technologies, not only for Canada, but globally. As I mentioned, many of these technologies are being used in the US. But how could you say that what would Russia or some of these Middle East countries would do? I mean, Iran said that they are not gonna do anything until they sign another agreement. So, I mean, it's all political games. I mean, so hopefully people, if they are really responsible, then we are gonna see it happen. But what I see also is methane emissions is opening a huge door in terms of economic prosperity. Bill Gates said that this business of reducing greenhouse gas emissions is gonna create an industry. It's gonna be bigger than building 11 Teslas and Amazon, Google, and Microsoft, and so many others. So essentially what he's saying that this would become the biggest industry in the world. And we Canadians, we have that opportunity to use our technologies and then become a leader and provide huge economic prosperity to Canada. So it's not only we can reduce methane emissions and create a brand for our oil and gas, which is really clean and much cleaner than the rest of the world, but also we can use that one for creating an industry, a sector of clean tech that could really hugely improve our economic prosperity in Canada.
Soheil, thank you. David, can you comment on the price cap of $30 per gigajoule in the recent BC hydrogen strategy?
$30, I'm not sure what is meant there. So maybe price gap. This is the gap between hydrogen and so what is it, $30 per gigajoule of what? I mean, there's $30 a gigajoule is, if you look at it in the diesel market, that's about, what is that, about $1.15 or something per liter, something like that. It's, that's a $30 a gigajoule. So maybe, we have, I suspect if you're making, especially in British Columbia, where they're looking more at green hydrogen production, there's
from hydro.
Probably, yeah, from hydro. The cost of the hydrogen is probably, more like $60 per gigajoule. So there's maybe a $30 per gigajoule gap, or $60, $70, $80 per gigajoule is what the hydrogen cost would be, higher heat value. And so then if that's what they're talking about, there is a gap. I think the gap is in Alberta, we're in the Edmonton regions in pockets. We have 3 areas in Alberta where we make a lot of hydrogen today. The one that makes blue hydrogen is in the Edmonton region, which is why we've started there. Fort McMurray makes a lot of hydrogen, but it requires a big pipeline for CO2 to find a place to store that CO2 to make it blue. And if the cost of that, I don't think it's anywhere near $175 a ton. I would argue it's less than that. It's because you'd be using pre-combustion capture with autothermal. You'd have different technologies. But Medicine Hat is the other region that they've got a lot of hydrogen production in that region. And I think there's geological sequestration potential around there, hasn't been built out yet. So I think that those places, we can do it, we can make it, there's not as big, there is a problem of a price gap now, but it's mostly because we aren't at scale. We haven't got it to a scale of supply and demand, right? So.
David, thank you. Another environmental question about NOx production when hydrogen and ammonia are used in combustion processes.
Yeah, so certainly NOx is an issue. I've been working with a group at the University of Alberta who's been doing hydrogen injection into diesel engines and looking at NOx production. And what I've been told and what's in the literature is that you can manage this. It's you got to keep the temperature from getting too high, and you can do that by how much hydrogen you inject, perhaps even how you inject it. And some people they see some real advantages of squirting some water in there as well. So putting some water into the injection, and it actually helps to in the combustion of the diesel as well. So I've been told by the diesel engine people, this can be managed, but it's certainly an issue that needs to be managed. Okay.
I think NOx is also an issue for oil and gas because of so many compressors that we have and they generate NOx. So we just actually decided that we are going to add NOx to that Can Eric facilities that I mentioned. So we are going to be field testing at zero cost technologies that would reduce NOx emissions.
We have another 3 or 4 minutes left, so if you could be quick in answering the next question and the one after that. Do you have perspectives on CO2 sequestration potential in Canada outside the Western Canadian Sedimentary Basin? This includes Ontario, Quebec, and Atlantic Canada.
Certainly, a little bit in southern Ontario, a lot of potential underneath Hudson's Bay, but it's kind of far away from where the people are. A little bit in the Gas Bay region in Quebec, some in Nova Scotia, maybe possibly some off the west coast in BC, but there's not a lot. I think for Ontario, which is the main interest and center, there is quite a lot of sequestration potential just south of the border. So there is a possibility there of just of sending CO2 pipelines for sequestration in Ohio or things like that, but they don't have near the potential that Western Canadian Sedimentary Basin has.
Soheil, any comments on that?
No, that was well taken.
Then the next question for you is, what percentage hydrogen can be transported in the existing infrastructure, including the compressed and heat affected zones at old pilots to require major upgrade and liners? I think you've answered most of that question previously, but do you want to just summarize?
Well, my sense is it's in the from talking to the companies, 5 to 10 to 15%, above 15%, 20, theoretically 20, but for safety margins up to 15 or 20%, which is only 15% is only 5% of the energy. So it's a good start, but it's not going to get us to where we need to go. So there's work needs to be done there.
Somebody asked about the possibility for the presenters, that's you, Soheil and David, to post your email and make that available for further questions, presumably.
Yeah, it's fine with me. I would be more than happy to share.
Okay, maybe put that at the end of your presentation which will be posted.
Yeah.
And you, David, as
It's
well.
on my pages. It's on page 1 and in the last page. Yeah.
Oh, perfect. Okay. There is a clarification on the earlier questions about the hydrogen price.
It's a long question. Maybe I can answer that offline if you want, if they want to.
Okay, let's do that.
Send to me, but that's all right.
And what is the critical immediate investment and government policy required to move forward with hydrogen?
I think we need to, I guess I would argue there needs to be decide where we need to make a decision of where we really want to go in this direction. I think the governments are aligned provincially, federally, multiple provinces, that hydrogen is a major part of our net zero future. But then we need to figure out where we should be putting the funding. And I would argue that the public funding needs to be to create the demand, the domestic demand for the hydrogen. But it needs to be, it's like any chain, a value chain is only good as its weakest link. And we've got to make sure we build the links that are weakest. And right now, the weakest link is on the demand side. We got companies producing low carbon hydrogen. We just don't have a demand for it. We need to build the demand.
Okay, I'm going to stop here just because time is up, and want to really thank both of you, Soheil and David, for, I think, making it a very, very interesting morning or afternoon, depending where you are. It's really great to have had you. I think this is an excellent webinar. I think people will be wanting to download your presentations. And as you saw, many people have many questions to ask, and we'll be contacting you by email for additional questions. So thank you very much. And at this point, I also want to thank Emmanuel and Anne-Marie, who have made it all happen so that it's become very seamless, and really appreciate their contribution. And you, the audience, who have stuck with us for a reasonably long period. We really thank you and for all the questions you've asked. So thanks, everybody.
Thank you, Eddie, and thank you all. Thanks.
Thanks.
Thank you. Bye.
Bye, everybody.
Bye.